Okay, continuing on with the test number 3, practice test number 3 for physics. Now, several of these examples have to do with the conservation of energy, and I've taken a bit of a shortcut with my notation here, and I've just noted that Ke equals Pe. The kinetic energy is equal to the potential energy. And the reason why I say that is because this is really just an extension of this formula, and we've got this on our note sheet, and it did, or I'm sorry, on our formula sheet, and it did come from our notes, that the work done by non-conservative forces, I should say, if work done by non-conservative forces equals 0, then what that implies is that the energy in the final position is equal to the energy in the initial position. Now, examples of non-conservative forces were friction, tension, push-pull forces, and those that are essentially not associated with with potential energy. So not associated with potential energy. Those are what we would call non-conservative. So in this particular situation, when we're talking about a pendulum that's swinging, well, the pendulum is swinging only because gravity is pulling on the weight of the object or the mass of the object at the end of its rope in this case. So the object is moving only because of conservative forces, aka gravity in this case. So if we consider for a moment that the initial position, and at least in this particular frame of reference, is at the initial position, which is at the bottom of the pendulum, whose height is 0, we have a velocity of 5 meters per second, and we would like to know what's the height that this object is going to swing towards. Well, we have a bunch of kinetic energy at the bottom of the pathway, and we have a lot of potential energy at the top of the pathway. So those two are going to be equal. The initial energy must be equal to the final energy. Whoops, I highlighted those backwards, but same statement is true. So if the kinetic energy formula is 1/2 times mass times velocity squared, and potential energy is mass times the gravitational constant times height, notice how mass cancels out, just like we saw the 1/2 that would cancel out immediately in a prior example. Mass is irrelevant in this computation, so we can isolate h by dividing both sides by g, and I have rewritten v squared over 2 instead of 1/2 times v squared. We make our substitution, and it appears that the object at the end of this pendulum should swing to about 1.3 meters, and that does look like a good choice for us here. Now with number 7, we see another similar question. We've got 3 balls that are launched from the top of a building. One is fired horizontally, second one is fired downward at an angle of 25 degrees, and the third one is fired upward at an angle of 60 degrees above the horizontal. If the launch speed of each ball is the same, which ball hits the ground with the greatest speed? Now in this problem, it may be helpful to note that all 3 clearly have the same potential energy. So potential energy of 1, potential energy of 2, and potential energy of 3 are all the same because they're identical to one another and they're all starting from the same position. Well, if all 3 potential energies are equal, then all 3 kinetic energies are equal. So kinetic energy 1, 2, and 3 are all equal. Then it may be worth noting that based on the definition of kinetic energy, which is 1/2 mass times velocity squared, if I were to solve for velocity, that is, multiply both sides by 2, divide by m, so we've got 2 times our kinetic energy divided by m, and then the square root. Well, if all kinetic energy and masses are the same, then all velocities must be the same as well. So generally speaking, since they all start at the same height, their gravitational potential energies are equal, and therefore their kinetic energies are the same, and by an extension of the definition of kinetic energy, we see that their velocities are the same as well. So it's kind of interesting and perhaps counterintuitive to most. If you've got a ball that's coming out, horizontally from a position, one that's being fired downward at a particular angle, and one that's being fired upward at an angle, by the time they strike the ground, they're all going to be traveling at the same velocity. In number 8, we have a crate that's 12.5 kilograms, and it's sliding at an initial velocity of 4 meters per second, then slides down a frictionless incline. That's good to know that it's frictionless, and it has the following properties. It's 4 meters in length and 3 meters in height. We would like to know the speed of the crate at the bottom of the incline. Well, what I've shown here is kind of the long way to show how to compute this, but essentially what we should recognize here again is that the kinetic energy of this system is equal to its potential energy, because the work that's being done here is done by gravity, which is a non-conservative force. It's also worth noting that there is velocity, constant velocity at the beginning of this problem, but no additional forces are involved. Because again, without a change in velocity, there is no acceleration. Without acceleration, there is no force. So we have no outside forces here. The only force that's doing any work is gravity. And so we could note quite simply that potential energy is equal to kinetic energy. And if we solve for V by performing the appropriate math to do so, the velocity of the object at the end is the square root of 2 times gravity times h. Now, in case you were unsure of that, or if you were thinking about this the long way, we might recall the free body diagram that looks something like this, where we have an object that's resting on a plane, and we have gravity that's pulling it down, and the plane is kind of interrupting the downward force of that gravity. And this downward sliding force, the projection, if you will, in this direction, is equal to this dotted line down below. And we can find the length of this dotted line by taking sine of the angle of the incline. So the angle of the incline can be reported here, even though we're technically measuring that angle here. So we've got the angle of the incline and the opposite side length of the right triangle that's formed by the normal forces, etc. The angle that's formed of the ramp is repositioned here in this right triangle. So the opposite side length of that right triangle, which corresponds to the force down this slope, is the force of gravity times the object's mass times sine theta. So, and one other thing to note too is that same theta value here and here, those two are the same theta values, does tell us the total distance that the object travels to. If I use sine of theta equals the opposite side length 3 divided by the distance that the object actually slides on this particular ramp, well, I can solve for the distance that the object slides by taking 3 divided by, let me think about that for just a second. Yeah, that was right. The opposite side length 3 divided by the hypotenuse d, that means that the hypotenuse length d is 3 divided by sine theta. So here we go, back to what I was saying about the long way around. We may consider the work in a system that's being done is equal to its force times the distance that the object travels. Well, here we now have the force due to gravity interrupted by the plane, the inclined plane. Here we have the distance that the object travels down that plane. And in the process of simplifying this, you'll notice that sine theta and sine theta will cancel, and we're left with just mass times gravity times the height, or the vertical displacement. And here again, if this represents our potential energy, or the work being done by gravity, then that should be equal to the kinetic energy at the bottom, and that also supports the claim we just made. So either way you think about it, whether you're using the traditional definition of work, being force times the distance traveled, or the notion of the conservation of mechanical energy, we end up with 7.7 meters per second as a result. Now in number 9, we have a toy rocket that is receiving some amount of energy from thrust. So with that being thrust, that's definitely a non-conservative force. It starts from rest on the ground and travels up to its maximum height before running out of fuel. So if we ignore any other outside, loss effects from burning the fuel, like losing mass because we're burning fuel, what is the maximum height? Well, here's the work that I would show for that, but this stems from the equation that says the work done by non-conservative forces is equal to the change in kinetic and potential energies, or the sum of those two, where kinetic energy change would be the final kinetic energy minus the initial kinetic energy, and same thing with potential energies, that the final potential minus the initial potential. And what's particularly interesting about this problem is that there was no kinetic energy at the beginning or end because the object wasn't moving. It was at rest on the launch pad at the beginning, and it's at rest technically because it's paused at the peak of its travel at the end. So there is no kinetic energy at the beginning or end of this, and there was no potential energy at the beginning either because the object was resting on the ground. The work in this scenario is simply equal to the potential energy at its peak. So the work that's being done by the rocket's thrusters is equal to mass times gravity times height. We know the mass, we know the gravity, and we know the work that's being done. So when we substitute those values, we ended up with 48 meters for height, and that's approximately 47.6. I reported 48 due to two significant figures. Now this next example experiences something very similar. We have the mass of a basketball. It's dropped from rest, so it had no initial velocity, so no kinetic energy, and it had a height of 1.5 meters above the floor. It bounces and travels up to a final height of 0.9 while it briefly pauses. So again, no kinetic energy there. Now we may note from a prior section that the work done by conservative forces is the opposite of potential energy. I should say the opposite of the change in potential energy, whereas the work done by non-conservative forces is the change in all energies, which is essentially what I've shown here at the start of my line of work. There was no kinetic energy at the beginning or end because the object was paused or at rest for a brief moment anyway at the very top of its travels, but it had no kinetic energy. We were dealing only with potential. And the potential energy at its peak was the initial position. The potential energy at the 0.9 meters was its final position. So if we make the proper substitutions, we then determine that the work that's being done is negative 3.8 joules. And so again, for the non-conservative forces, this would not be gravity, but most likely friction or air resistance or something like that. Okay, I think this is a good stopping point for this video, and we'll pick up with the next questions in the next video. Thanks for watching.